Yeah.
Yeah. So, okay, so problem number one basically gives you a specific drawing from one reference and one source, which I have mentioned. And what it actually asks is you have to identify all the geometric features. Geometric features basically means when I say features, if you have been following the lectures about the GD&T features, basically that can be measured using vernier caliper, two opposite ends of the vernier caliper. So you have a shaft diameter of certain radiuses or certain diameter. You have a tapering in there. So whatever the features, you have an undercut in here. You have basically an undercut here. You have a chamfer. So whatever the features that you can identify from looking at this drawing, you need to identify that. And you need to identify any GD&T specification. If you feel like there is any GD&T specification in this drawing, you have to identify the GD&T specification, which is basically you have to go through the the slides or the PowerPoint slides in the textbook chapter to understand what this symbol represents, what this tolerance amount basically corresponds to, what is this letter symbol represent. So all the GD&T symbols need to be identified and explained properly. And then types of limits and fits. So we actually gone through that in the last lecture, I believe, about what type of fits and tolerances are there if a specification is provided. So for example, if you look at this specific drawing, you can identify certain symbols like H11, M7, H12, so N5. So what this basically means here, what this N5 basically means. So if I say N5 and corresponding to 75 diameter, what is the minimum size and maximum size, upper limit and lower limit for that? So generally people do not give you 75 plus minus certain amount. They specify using these symbols and that represents the limits and fits. Now, what does N5 corresponds to? You have to go through the chart. You have to find out what should be the upper diameter and upper limit for the diameter and the lower limit for the diameter. Same for what is H11 basically means here. So you have to go through these calculations for the limits and fits and find the max size and min size. Is it making sense, guys? Are you following it?
Yeah.
Yes.
Great. So type of thread specification. So if you see their drawings call for any thread specifications in here, you basically have to identify that as well. And identify any surface roughness specific. If you see that any specification, anything in the drawing represents the surface roughness, you have to identify what that symbol is, and you basically have to identify that as well. So this is nothing but the interpretation of the drawing. So you have given the drawing and it's just a typical drawing that you will obtain or you will be encountered with or you will actually face in the shop floor. Or if in any design department, if you work in any organization and you come across any drawing, this is a typical drawing with details. So you basically have to identify different details that are provided in there. So the point here is that can you identify these details and can you understand the meaning of those details? So that is the whole objective of this problem set or problem number one. Make sense, guys? Yeah.
Yes.
Yes. Pretty much we're just pretty much describing everything that's in the drawing, right? Like explaining.
Yes, exactly. So you are explaining all the different dimensions, different symbols in here. So you have to basically understand what this basically means, what this taper 1:10 basically means. So you have to identify all the different parameters or specifications that are there, mention the drawing, and identify what it actually means. So it is just an interpretation of the drawing. I think.
Okay, that makes sense. Thank you.
Welcome. Any other questions in problem number one if you are not able to understand it yet?
Yeah, can you remind me what the surface roughness specification, or can you, what was the symbol for that, please?
So you have to look it yourself. You have to do some homework by yourself. So I'm not going to tell you exactly what it means and where is it. So you have to do that as part of the homework actually.
Okay, thanks.
Okay. Yeah. Okay. Any other questions, guys? If not, I hope then the problem number one is now clear, that what you have to do, you have to basically identify the drawings and you have to answer the questions that are there, which basically relates to understanding the different specifications and different parameters and uh, different GD&T symbols that are mentioned in there and what they actually mean and what they actually represent. Make sense to everybody?
Yeah.
Yes.
Great. Problem number two, standard question. Read the discussion about MMC and LNC. There was some question that this specific link does not have the symbols. Somehow the symbols are not loading on the website. But if you have read the chapter or you have followed the lecture slides, then you don't need the symbols as well. You basically can go and understand from the text. But even though you don't need to refer that website, it is just for the reference. You can even read your chapter number 20 from Shigley's textbook. That will give you enough information about what the MMC and LNC basically means and how it is used in actual applications. So that is problem number two. Problem number three is basically same standard problem we actually went through in the class. It's about what is the framework for implementing GD&T. And the point here is that you guys are expected to take one drawing out of your senior design project and implement the GD&T framework that I have mentioned, the 5 steps that are basically mentioned in here. You have to use those 5 steps and see if you have to specify GD&T symbol in your drawing, how would you represent it? So for each group, you are not like, if the group has 5 members, all the 5 members are not going to work on only one drawing. So if you have 2 or 3 drawings, you are going to work on different drawings and identify those features. Of course, you can collaborate and understand how to implement that, but I would not suggest that each one of you will come up with only one drawing setting. So please make sure that the drawings for the group members should be different as possible. If you do not have 5 different drawings, it's understandable. But if you have different drawings, please work with the different drawings for implementing GD&T symbol. So that is just an exercise for you to practice the framework of implementing GD&T in your drawing or in the parts that you are going to fabricate. So that's problem number 3. And problem number 4 is basically the type of fits and tolerances we were doing in the last lecture, which is to find out what is the torque carrying capacity and what is the stresses, maximum stresses that will come because of the specific type of fit, which is H7, S6. So based on this specification, can you find the hole diameters, the minimum and maximum diameters, and the shaft minimum and maximum diameter? You can find the interference, what is the amount of interference you're going to have, and based on that interference, you can calculate the stresses that are coming and the torque carrying capacity. So we actually went through this in the lecture itself. So that is basically the standard question. Let me know if anybody has any questions on these 4 problems. So you guys are good so far?
Yeah, you cleared it up.
Great, thank you. So let me then go to our lecture slides, which will be the continuation of the belt drives. And before we start, again, any questions and concerns regarding anything from anybody? Is everybody good so far?
Yeah.
Great. And as I mentioned, that if my audio keeps on breaking and it's not making sense what I'm talking about, then please interrupt me and please let me know so that I can repeat what I was discussing, so that you guys do not lose on the information I was trying to pass it on. So please interrupt me and let me know that my audio is not, or quality is not clear, or somehow my voice is breaking and it is not making any sense. I will try to repeat it again. So having said that, we will actually go through some of the introductory slides and then we will focus on the design aspect. So what we actually focused on last week is understanding and selecting a specific type of belt drives for transmitting power. And we saw that there are different options. We have V-belt drives, we have flat belts, chain drives, tooth belts, and so on. The difference between the flat belts and V belt drives versus the chain drives and tooth belts is these drives, neither the V belt, neither the flat belt has teeth or serrations, which basically means there are chances for slippage. And if that happens, then the driving pulley and the driven pulley can have mismatch in the angular velocity ratio. So you can have different angular velocity for the driving side and different angular velocity for driven side. But the point is that they remain constant if you work with chain drives. If you work with chain drives, then the ratio between the driving and the driven will remain constant. But that the constant angular velocity ratio cannot be guaranteed in flat belts and V-belt drives because it is all friction contact. And because of the friction contact, you have no control that if there is an overload, if their torque is exceeded, then you may have slippage, and there you don't have any control. But in case of chain drives and tooth belts, you do have control because there is a serration and the teeth are in engaged position. So there is no there is no possibility of slipping of this chain on top of that. So there will not be slippage. And if there's no slippage, then the ratio of the velocities of this pulley or this gear to that gear, this sprocket to this pulley will remain constant. So that is the basic difference between the tooth drives, belt drives versus non-tooth belt drives or non-serrated belt drives. And then we actually went through certain characteristics about the geometry of this flat belts and round belts, V belts. So these are certain specifications from the manufacturer about what type of geometric characteristics they have. Then we went through the material aspect, that what are the common materials that are used for the belt drives. For flat belts, we have like generally urethane and rubber impregnated fabric, which is reinforced with steel wires to have the necessary strength for transmitting the torque. You generally have efficiency of around 98%, which is almost similar to gear drive for flat and round belts. So if there is no torque overload or there is no slippage, and you have properly selected a given for a given application, you have selected proper belts, you have properly sized them, then you will get an efficiency of power transmission of 98%. There will be no such losses that you will experience or you will encounter because of the friction. So most of the power from the input side will be delivered to the output side with very negligible losses. So basically you have efficiency almost similar as gear drives. In addition to that, the advantage of this flat or any type of belt drives is that you can accommodate longer center distances between the two shafts, the input and output shaft. So if you have a longer center distances and you do not want to have a gears engaged between the input and output shaft, you can transmit the power using belt drives. So belt drives allow you to have the option of greater center distances between input and output shaft. And at the same time, the efficiency is almost similar to gear drives. Okay, so thereafter, we will now focus our attention on the mechanics of the belt drives, like what type of forces that are actually coming in there, what type of belt tensions that are there, and what is the role of initial tension in the belt. How can we make sure that the initial tension actually stays in there in the proper amount? So we will actually focus our attention on that. But before actually going through that derivation, I would just focus on these couple of slides here, and which are based on the simple geometrical aspect of the belt drives. It basically says it is an open belt configuration. Basically, you have a smaller pulley, which is all in general, it is called, generally this smaller pulley is called as the driving pulley. The bigger pulley is called as the driven pulley. So this is the driving side, is the driven side, and the belt actually wraps around the pulley and it enters into the contact with the pulley at this point, and then leaves the contact at this point. So the angle of contact between the belt and the pulley from this point to this point, from the point where it is entering into contact and the point when it is leaving, is called as angle of wrap. And this angle of wrap plays an important role because this angle of wrap determines how much surface of the belt is in contact with the pulley. And that surface, whichever is in contact, will actually helps in transmitting the torque, because there is a friction between the two surfaces. So the greater the area you will have, or the angle of wrap you will have, you will get more contact area. That means you have more frictional friction frictional force that is going to help you to transmit the necessary amount of torque. So that basically helps to the amount of angle of wrap helps to increase the torque transmitting capacity. So that is purely dependent on the geometry. So if you know the diameter, the smaller diameter, the bigger diameter, you can calculate what will be the angle of wrap by knowing the center distance between the two shafts or two pulleys, the smaller diameter and the bigger diameter. So if you look at the expression, and these are all purely trigonometric expressions. So this is theta d, the angle of wrap at the driving side pulley, is basically given by this expression, which is only dependent on bigger diameter, smaller pulley diameter, and the center distances. So based on these three parameters, you can find the angle of wrap at the driving side and also the angle of wrap at the driven side. So, and that is basically is going to be important for our calculation of the belt tensions that we will see in a short while from now. Any questions from anybody so far? So everybody's good so far?
Professor, what does L stand for?
Okay, so the L here basically stands for the, let me actually see from the figure what actually L stands for. So I am guessing here because I don't exactly know or from this schematic, but it basically shows the centered distance from the center distance from this point to this point. So whatever, am I making sense here? Let me see. Okay, I will come back to this specific part. I'm not seeing in the schematic what this L represents. The important parameters are the angle of wrap. Let me actually see what this is.
Could it be the length of the belt, possibly?
Yes. Thank you for helping me out. So yes, it is the length of the belt from going from this side, total length of the belt, which is wrapping the pulleys to pulleys. Thank you for, I missed that point.
The length from the different angles of wrap of each side?
Total length of the belt. So if you basically see if you see, look at here, this term, capital D times theta D, which is the angle of wrap times the radius. This basically tells you the circumference of the belt that is in contact with the bigger pulley. This term, small d times theta d divided by 2, gives you the length of the belt from starting from this point to this point. It is r theta. It's something like that. So if it is circumference of the pulley which is in contact with the belt. So these two lengths are basically given by these two expressions, and this expression here basically is this contact from here to here and twice of that, because you have the top side and you have the similar distance on the bottom side. So this perpendicular distance between these two points plus the wrap of the belt along the pulleys. Make sense?
Okay. Yeah, it does. Thank you.
Yeah, thank you. And thank you for helping me. So this L represents the total length of the belt around the pulleys. So, okay, this is again a purely geometrical construction. And yeah, it is basically, it will be basically important when you will have to purchase a belt or you have to specify the belt length. So what we will be focusing our attention on is what should be the width of the belt, what should be the thickness of the belt, and what should be the stresses that are coming into account. But if you have to also purchase the belt for the given center distances, you also need to know what should be the length of the belt you should purchase, and this specific parameter or this specific expression will help you to get that information. Okay, so again, any other questions and concerns, guys? I believe if everybody is good so far, so let me share the document camera. So hopefully this is visible to all.
Yeah, sure.
So yeah, great. So what we are actually going to see here is that can we, how do we design or how do we get to know what should be the width and thickness of the belt and what should be the material properties of the belt when we are going to when going to select a belt drive for a given application. So what I'm drawing here is one schematic of belt drive from the driving side to driven side. So let's say this pulley is this driving side, this is rotating clockwise, and this is an open belt configuration. So you also have a clockwise rotation of the belt. Now, these are the tensions that I'm actually representing. So if I look at this specific portion of the belt drive, you will see that the tension at this end is basically represented. I'm representing it F1. It is a tension on this side, and there is a tension, different tension on the other side. And the belt that is passing through this pulley and leaving the contact here must have a different tensions on the two sides. So that basically means you will have one side of the pulley or basically is a tighter side and one side will be loose side. So can you guys identify what should be which one will be the loose side and which is the tighter side? Okay, before I actually ask you this question, let me ask this question to you guys. So do you feel like the tensions will be different or will be same?
This is under when everything's rotating, right?
Yes.
I think the top will be or that's, no, wait, sorry. The bottom will be the tension side, no?
So, okay, we will come to that question later, which one will be tension and which will be more or which will be less. But do you guys feel that these two tensions on the two sides of the belt will be different? If you actually look physically, basically you have the belt and it is passing from, it is just the same belt. It is passing it is in contact with this driving side pulley and it is wraps around and it leaves the contact. It's the same belt. So do you think that they will have a different tension on the two sides?
No.
They'll be different.
Okay, so the answer will depend on whether there is any torque transmission. If you do not have any friction on the pulley, if the pulley is frictionless, then there is no way that you can have different tension on the two sides. Do you see what I'm saying, guys?
Yeah, that makes sense.
Because of the friction between the two surfaces, you will have different tensions on the two sides. The friction is basically causing the tension on two sides to be different. So because of that, you will have different tensions. And because of these two different tensions, the amount of torque that can be transmitted from one side to another, for example, if you have to find a torque being transmitted from this pulley to that pulley, so this is, let's say, number 1 and this is number 2. So if you have to find the torque being transmitted will be given by the difference, let's say the difference in the two sides of the tensions, delta F times the radius is d over 2. So this is basically the torque that basically is going to be transmitted from this pulley to the next pulley using the belt drive, and that will depend on the difference in the tension on the two sides. If there are no differences, then you cannot have any torque transmission taking place, and the torque transmission is taking place because of the friction. If there is no friction, there is no reason that you will have tensions, two tensions which are different. Make sense to everybody so far? Yeah. Any
Yeah.
questions from anybody? So you guys now agree that these two forces or these two tensions will be different, right?
Yes.
So which one will be
If there's no torque transmitted, then yeah. Right?
opposite? If there is torque transmitted,
Okay.
yeah, if there is torque being transmitted, then there needs to be delta F. If delta F is 0, then the torque transmission will be 0.
Gotcha. Thanks.
Great. So you guys now agree that they will be different amounts. So F1 and F2 will not be same. Now the next question is that which one will be greater, whether you think F1 will be greater or F2 will be greater.
Does it depend on which one's driving it?
Depends on which one is driving it. That's true. And we are basically considering this as a driven pulley. So in that case, can you identify which one will be the bigger one, bigger tension?
The top?
F1.
The bottom, right?
So if this is the driving pulley, so this is your driving pulley here. So external load or external agency, which is a motor or some other source, it is basically driving this pulley. So this is a driving pulley. So what you have to basically then look at is, and this, whatever the logic I'm basically trying to explain here or present here will be same applicable for the driven side as well. So let's say for looking at driving pulley, this pulley is trying to climb on the surface. So when it is trying to climb on the surface of, so imagine that this belt represents a surface on which it is trying to climb on. So this is basically trying to climb on the surface and it's stretching it. So if you look at physically that you are present in here and you're rotating it along with the pulley, when it comes in here, it is trying to stretch this belt along with it. So this is basically going to be the tighter side. So this is a tight side. And if you look at this, when you actually rotate it, you are basically leaving the surface. The belt is leaving the surface. So this will be the loose side. The same argument will hold in here, which is your driven pulley. If you look at this spec, the pulley is again, if you are looking at here, the pulley is trying to, I mean, this is a driven pull side. So basically you are having a different now. You are basically, since the argument that we are presenting about a driving pulley, this is basically the F2 will remain the same. So driven pulley will not be having the same argument that we were actually having for the driving side. So for driving side, the tight side will be the bottom one and the loose side will be the top one. But here you will see that this pulley is trying to climb on the surface of this surface, but this is a driven pulley. So here that argument will not hold, but that argument will hold only when we have to consider the driving pulley. Is it making sense, or am I just losing you somewhere or confusing you?
It makes sense.
Yeah.
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 Anybody has any confusion, please let me try to explain again. So we have to first look at which of the two pulleys is driving and which one is driven. So this is a driven and this is a driving side. So at the driving side, we have to look at how the pulley is trying to stretch the belt on and wrapping it on itself. So if you look at this driving side pulley, the pulley is trying to climb on the surface of this belt. If I look at this surface, and is trying to stretch this belt and trying to wrap it along with itself and leaving it here. So the point it comes in contact with the belt becomes a tighter side, and when it is leaving, it is basically a loose side. Only true when we are looking at a driving side, not true when we are looking at the driven side. And once you have identified a right hand side and tight side and loose side, this will remain the same here. So you will have F2, the same tension, because between this point and this point in the belt, there is nothing which is changing the tension. The tension remains the same. So F2 remains the same all along. F1 remains the same all along, though nobody is changing the tensions between this point and this point. Only when this belt comes in contact with the pulley, the tension keeps, the the tension in the belt actually changes, and it changes to F2, and when it leaves with F2 tension, remains there, and F2 remains the same. So we are just focusing on the driving side here, and then we identify the neutral side and loose side. Make sense or not?
Yeah, it makes sense.
Good. Any questions from anybody if you're not getting that? So here, if there are no questions, then delta F basically means here F1, if this is the tighter side, the F1 is greater than F2, then F1 minus F2 times G/2 is your torque being transmitted. So this is also, I mean, mathematically also you can, or from free body diagram, you can identify tight side and loose side. If you draw the free body diagram of this pulley itself, you apply a torque from the motor, you get a force, and this is the diameter small d. Now, if an external agency, the motor here in this case, the motor is applying or providing a torque to the driving side. This is a driving pulley, right? It's a pulley which is getting some torque from external agency. So the motor is delivering a torque to this pulley. So in that case, the torque being applied on the pulley is clockwise torque. Now, if I have to balance that using the tensions, which force will be maximum? I mean, if you look at the free body diagram, this has to be in equilibrium, right? At a specific instant of time, this has to be in equilibrium. This pulley is not going anywhere. It's just staying in there. So of course, there are some reactions here from the mounting pin wherever the pulley is mounted. So there will be some reaction forces. I'm not drawing the reaction forces in here at this point of time. I'm just drawing the torque. So let me actually, just for the sake of completeness, let me also say the reaction forces Rx, Ry, and Rx. So these are the reaction forces from the hinge, from where the pulley is mounted. So I'm just isolating this pulley and drawing a free body diagram of the pulley. So this is just a free body diagram of the pulley. So if you draw the free body diagram, the Rx and Ry are the reaction forces of the hinge or the pin from where the pulley is mounted. They are reaction forces. Torque is T is the external torque transmitted by the, or supplied by the motor. So external torque supplied by motor. F1 and F2 are the forces or tensions from the belt. Now, if I have to do the moment balance of this pulley using, for a given instant, summation of moment equals 0, that basically means that the torque T plus the movement due to the forces, which will be F2 times d/2 minus F1 times d/2, this is d, or F1 times radius, should be equals to 0, isn't it? Are you guys following it?
Yes.
Yeah. So it basically will give you the same expression which we were, which you started with, and it basically means that F1 is greater than F2. If T is the clockwise, then F1 is basically greater than F2. So basically it means that this is the tight side and this is the loose side. So this is just a mathematical way of understanding which one is the tight side and loose side by doing the force balance and moment balance. But just physical argument, you can basically see that the pulley is trying to climb on the surface of this belt, so it becomes tighter side, and leaves the surface and it becomes the loose side. So both basically works the same, argument works in the same manner. Yeah. So are you guys with me?
Yeah.
Yeah.
Okay. Okay, great. So having said that, uh, what we need to know next is how to relate the tight side tension and loose side tension with the angle of wrap and the friction. So what we have to do next is relation between the tensions on the two sides of the pulley, and the amount of angle of wrap of the belt surface, angle of wrap of the belt around the pulley. So how can we relate the tight side and loose side tension with the angle of wrap? So one relationship we actually know that this is the relationship between the external torque being supplied to the smaller side or to driven side pulley. And we know that if you know the diameter, then tighter side tension minus loose side tension will be your times the radius will be your torque. Now to find the relationship between the two tension, the two sides, what we have to do is we have to basically look at differential element of the belt that is in contact with the pulley. So let's say this is your smaller pulley. And the belt is actually going being wrapped and it's leaving the contact. Same way it is basically leaving the contact here. So we are focusing on a differential element of angle subtending an angle d theta starting from let's say a theta. Theta is basically the point at which the contact starts. So if we actually look at this differential segment of the belt drive and we actually try to identify all the forces that are actually acting on it, then what we will see that this element of the pulley or the belt, sorry, will have this type of forces. So it will have forces on the right hand side, it will have some forces on the left hand side. Then because of the contact, it will have a normal reaction force with the pulley, let's say it's given by Dn. Then it will also have a centrifugal force because this belt has a certain mass, this differential element of the belt has a certain mass, and this is rotating at a speed omega. So if the pulley is rotating at an angular velocity omega, then there is centrifugal force attached to associated with the rotation, and that can be given by the mass of the belt, differential mass, which is m times r d theta, which is basically the mass. If this mass is mass per unit length, then m times r d theta is basically going to be the mass of this segment times r omega square will be the centrifugal force. So centrifugal force acting on this segment, there's a normal reaction, and because of the friction, there will be a frictional force. Now, let me ask you about that. So where will the direction of the frictional force would be? It will be tangential, but it will be in this direction, or it will be in this direction. So this is my driving side pulley. This is rotating clockwise with an angular velocity omega, and what I am asking you that the frictional force will be tangential to the surface of the belt and the pulley. Now, whether the frictional force will be acting on the left-hand side or whether it will be acting on the right-hand side. So can you help me to find that out?
Does it oppose omega?
Yeah, it will be opposed on omega. That's a good argument, but at what which component will get that, which experience that opposing to omega?
The tight side of the.
Okay, so there are two surfaces here. One is a belt surface, one is a pulley surface, right?
Oh, okay.
Pulley is rotating. So pulley is rotating. That means it is trying to rotate omega, and it will experience a friction force which will be opposing that omega. So the pulley will be experiencing a friction force going in the left-hand direction. But on the other side, there will be action-reaction pair. The belt will be experiencing a friction force like this, because for related to the pulley, the belt is going this way. Sorry, going is left hand side. So the friction force will be acting right hand side. Does it make sense to everybody? This is the frictional force, coefficient of friction times the normal reaction. This is the frictional force acting on the belt, not on the pulley. There are two surfaces. So if I look at the two surfaces, so this is my pulley. Yeah, let's say this is my belt and this is my pulley. So since it is rotating clockwise, there will be, because of the belt, there will be friction force on the pulley acting opposing the motion here. But on the belt, it will be like this, because for the belt related to the pulley, the belt is going, is basically slipping out. So it basically experiencing a force, friction force in the right hand direction. Let me know if it, are you guys are able to get that? This F, this small f is your coefficient of friction. And you know how to find the frictional force. Coefficient of friction times the normal reaction. Our normal reaction is dn, which is given by this small dn. So this is a normal reaction, and coefficient of friction times normal reaction will be the frictional force. So friction force acting right hand side or left hand side. If I'm working on the free body diagram of the pulley, then the friction force is acting on the left hand side. But if I'm working on the belt, it is acting on the right hand side based on the assumed rotation. Are you guys with me so far?
Yeah.
Yep.
Anybody is not following it or is having any questions? Okay, if there are none, I mean, please let me know if you have any questions or any confusion. I will try to explain again. And if you are missing some information, please let me know if I will try to explain. Assuming that you have no other questions. So what we have to do next is looking at this differential segment of the belt and writing the force balance equation. So summation of F of normal equals 0 and summation of F tangential. So normal means normal direction, tangential direction. So summation of all the forces in the normal direction equals 0. So if I do that, but I will see that d of n plus d of s plus, sorry, minus f, this angle is d theta over 2. This angle is d theta over 2. This angle is d theta. So minus f plus delta f sine d theta over 2 minus f sine d theta over 2 equals 0. We don't have to write down all these expressions. This is already there in the textbook. And just focus on these expressions and try to explain that how we actually get that. So if you understand the expressions, then you go back and read the textbook, it will be easy for you to follow. So what I'm doing here is I'm just taking a differential segment of the belt. Remember, the belt is wrapped around the pulley. It is entering into contact in here and then it is leaving the contact. That's what we actually saw a while ago. So if I take a very small segment of the belt and try to identify the forces, I actually identify the forces like the normal reaction on the small segment, that is why it is dn, the centrifugal force because of the mass and which is rotating with the angular velocity omega is mr d theta mass times radius times omega square. This is mass. Mass is per unit length. This m is mass per unit length times r d theta. R d theta is the length of this differential element. So this is the centrifugal force of this differential belt element. Frictional force, which will be coefficient of friction F times the normal reaction, and the belt tensions. I don't know what is F1 and F2 at this point of time because we are working on differential small segment. So I assume that I have one tension F here on this side and a small different tension of delta F on the other side. And then what I do, I take all the forces in the normal direction and sum them up. So if I look at the normal direction, it is the forces that are acting at dn, ds in one direction, this dn plus ds, and then component of this basically normal to the basically the component of force in the normal direction. So if I create the component of this force in the normal direction, it will be f plus df sine d theta over 2 in this direction, in the opposite direction. That is why it is minus f plus df sine d theta over 2. Similarly, the component of force f in the normal direction would be f sine d theta over 2. negative F sine d theta. Summation of all should be 0 for the equilibrium. So I just put it equals to 0. Let me know if it makes sense to you.
Yeah.
Or if it doesn't, just let me know. I'll try to explain again. Any portion you are missing or you are not following it, please let me know. Everybody good so far?
When you say normal direction, you're referring to where the belt is interacting with the
yeah
pulley?
this small segment of the belt interacting with the pulley. So this is the normal direction of the
Okay.
yeah. This is the normal direction. And this is the tangential direction where the friction force is acting. This is the tangential direction. Got it?
Got it. Thank you.
Great. Thank you. Okay, so if you are okay with this expression, can you guys help me to find the or write the expression for tangential force? Summation of F tangential equals to 0. Can you help me to write the expression for that? Just looking at this figure or this image.
Would be
So what are the forces? Yeah, go ahead. What are the forces in the tangential direction?
I think it would be F times d theta over 2. F times d theta.
Small f or capital F? There are two F's here. Which F you're talking about?
Oh wait, sorry. Yeah, so it's capital F times cosine of d theta over 2.
Perfect. Then
and then minus F plus delta F in parentheses times cosine of d theta over 2.
Yeah, okay.
And then I think plus the friction F, small f, times dm.
Yeah. And then
I think that's it, and it equals 0.
Perfect. That's perfect. So that is, thank you. That is the correct expression for all the forces in the tangential direction. You just take the component of this force in the tangential direction, F times cosine delta theta over 2. Then similarly, you take the component of this in the tangential direction, which is F plus delta F cosine delta theta over 2 in the negative side. And then friction coefficient times dn. So that has to be equals to 0. Now, because we are working with small angles, so you have to make a small angle assumption, which basically means cosine b theta over 2 basically goes to 0, and sine b theta over 2 basically becomes d theta over 2 under small angle approximation. Right? Everybody is with me?
Yeah.
Yeah. So with that, if you actually plug in this approximation in here, plug in the value of dS, expression of dS centrifugal force in here, you will actually end up with an expression about the tight side tension and loose side tension. So let me actually write that down here. So when you solve these two equations, now I'm not going into the solution. I'm just giving you showing you the steps, and basically we write the steps, and thereafter you will end up with a differential equation. You solve the differential equation with the proper boundary conditions. What you will actually end up with is a belting equation, and that is basically given by this. This is the expression you will end up with after you solve these two equations. And because when you solve these two equations, you will end up with a differential equation, and with the boundary conditions, necessary boundary conditions, you will end up with this. This is the final outcome of working through these two expressions of normal forces. Summation of normal force equals to 0 and summation of tangential force equals to 0. So this is a belting equation you will get. What is F1 here? F1 is a tight side tension. F2 is a loose side tension. Exponential, this small f is the coefficient of friction. This theta is your angle of wrap. So angle of wrap so this is the angle of wrap, total angle of wrap that you will get for the smaller side and for the bigger side. So this angle of wrap you can obtain from the geometrical construction. We actually saw in the PowerPoint slide, that you can find the angle of wrap for a given geometry. So you can find the angle of wrap, you can determine the coefficient of friction depending on the belt material. The tight side tension, the loose side tension are given by these F1 and F2, denoted by these two symbols, and Fc is a centrifugal force, and it is given by m, mass per unit length, times r squared times omega squared. So this is the expression, and if you know the mass per unit length of the belt times the radius square times omega square, so that will basically give you the centrifugal force. So given this will be the belting equation. That is the most fundamental equation to understand the mechanics of the belt. So let me know if you guys are following this, following all the symbols in mentioned in here in this expression.
The the variable in the x in the exp, is that a small f or a big F?
It is small f.
F theta.
Yeah, small f times angle of wrap.
Okay.
So final outcome of solving these two differential equations, which I have not actually gone through the mathematics of that part. I mean, you can refer to the textbook and see the mathematics behind the solving these two equations. But solving these two equations, what you actually get is the final outcome, which will be the one that we'll be using in our design calculation. So if we have to find out, we have to find what should be the belt material we should be using, and what should be the tensions on the belt that needs to be provided. So this is the equation we'll be referring to. Okay, so that is basically comes from the solution of these two equations. So let me know if you have guys any questions so far. So assuming there are no other questions, so let me actually work on this and show you how to use that equation for your design calculations. So what you actually get is what we call as a belting equation is F1 minus Fc divided by F2 minus Fc is equals to exponential F times theta. F is your coefficient of friction. This is angle of wrap obtained geometrically. Let's see. F1 is tight side tension. F2 is loose side tension. And Fc is the centrifugal force because of the rotation of the belt and along with the pulley. So again, drawing the schematic of the driving side and the driven side. You know the small diameter pulley, and you know the bigger diameter of the pulley, and you know the center distances. This is the center distance C, and based on the rotation of the pulley and the driving and driven side, this is your loose side tension, and this is the tight side tension. So this much everybody is now agreeing with, right? So how to do the design, how we integrate this equation in our design, design of the belt rise, or finding out what type of belt material and whatever belt cross section we'll be using. So I'm going to give you now schematic, basically steps that you need to follow here. So for example, you have an input shaft here and an output shaft, the center distances are known to you, right? So given that you know that the input, this is the input shaft, location of the input shaft, and this is the location of the output shaft. So if you know the location of the input and output shaft, that there has to be certain constraint, there has to be certain constraint that they needs to be separated by certain distances, then how to move forward with designing a belt drive for that. So for first thing that you have to find out is that what is the velocity ratio you need. So what is the velocity ratio you need will help you to find that what will be the ratio of d over small d. The velocity ratio between the input shaft and the output shaft is governed by the ratio between the bigger diameter and the smaller diameter, right? Are you guys with me?
Yes.
Yes.
Yeah. So as a designer, what you can begin with as an iterative step, you can start with a small diameter. You can pick standard, smaller available diameters. And basically you can start with a very smaller diameter that is available. And based on that, you can find the capital diameter, capital D, based on what the velocity ratio is needed. And this, whatever the diameter you have assumed. So for example, this is start with this assumption, start with assumed value. Start with assumed driven side pulley diameter. So if you start with this assumed diameter and you know what the velocity ratio is needed, then you can find what will be the bigger diameter, capital D for that arrangement is needed, right? Everybody's with me so far. And if you know the center distances, because this is your constraint, that what should be the distance between the two shafts, so you know what capital C is. Based on that, what you are going to do is step number 1 is calculate the angle of wrap for this arrangement. Angle of wrap. The angle of wrap is phi d, and also let's say phi capital D. Phi d basically means that it is the angle of wrap at a smaller side, and this is the angle of wrap for the bigger side, and they all depend on the smaller diameter, bigger diameter, and center distance. We know, we actually saw that expression. It is basically purely geometrical, obtained from the purely geometrical construction, and you can calculate the angle of wrap from that. Is it clear to everybody so far?
Is that a capital D on the right side?
Yeah, capital D, small d.
Oh, okay.
Okay, everybody is following it so far?
Yes.
Great. Step number 2. So step number 2 is you would also need to know how much amount of power needs to be transmitted. Or what is the maximum power to be transmitted? Or maximum power to be transmitted. So for example, you need to transmit 20 horsepower from input to output. Now the torques will be different, but when I say torques will be different, it is basically the driven side and driving side will be different, having different torques. And let me explain you why in a bit, in a short while. But what is remaining constant is that you are supplying a power to this pulley using an external motor. So you're supplying a 20 horsepower, or maybe let's say 100 watts, whatever the units you actually, or values you actually take. So you're delivering a power to this motor, or through the motor to this pulley. And that power, you are expecting a power basically goes from the input side to the output side with minimal losses, without any loss, right? That's what your transmission is all about. The purpose or the role of the transmission, here we use the bell drive transmission. The role of the transmission is it delivers the power from input side to the output side with minimal losses. That's what the efficiency of the transmission is. And if it is almost 100%, that means whatever the power you are delivering, so whatever the power in, P in, should be P out, output power. So there will be no losses, then P out and P in is equals, should be equal, right? If not, then you have the efficiency given by P out divided by P in. That will be your efficiency. Output power divided by input power. So whatever the output shaft power is divided by the input side power will be your efficiency of the transmission. And if the efficiency is close to 100%, then basically means P out and P in are almost equal, right? Are you guys following it so far?
Yes.
Yeah, it need not be 100%, it can be 90%. Then you basically know what is the power output. It will be 90 eta times P input. That's what it is going to be. So that is what the efficiency is. Efficiency is the ratio of the power from the output to the input. So you're delivering a specific power and you are basically finding out what is the maximum power to be transmitted. That you should know as a designer, because that's why how you are trying to go with the design of transmission, bell transmission. So let's say that P max is given to you. Now P max is basically your input power, input max power, and how the power is related to the torque and angular velocity. Can somebody tell me what the expression should be for relating the power with the torque and angular velocity of the pulley? So power is torque times omega. T input, omega input. This is your input side. And this is your output side. Are you guys getting right what I'm trying to explain here? Yeah, everybody is with me?
Yeah.
Yeah.
Cool. So based on the max power, and if you also know what is the angular velocity of that or the angular rotation of the pulley side, so you can calculate the input torque, input max torque as P input max divided by omega input. What is this angular velocity? Because if you're delivering a torque using a motor or engine, you also know at what RPM they are delivering that in power. Is it 1500 RPM, it is 500 RPM, it is 100 RPM, whatever RPM the input side or input shaft or input side source is providing, you already know that rotation speed of the motor or engine, whichever agency is supplying the power. So you can find the maximum torque from these calculations. Is it clear, guys, so far?
Yeah.
Great. Step number 3 is select a belt material from catalog, manufacturer's catalog. Just like you have to select a material, whether it is steel, aluminum, copper, plastic, whatever material you begin as a designer, you start with your design calculations, you have to select a belt material similarly from manufacturer's catalog. Manufacturer's catalog. And that will give you F1 allowable. What is F1 allowable? It is basically the maximum tension, maximum belt tension that is allowed. Otherwise, if you exceed this tension, and what this one subscript represents is a tight side tension. Remember, F1 is a tight side, F1 is a tight side, and F2 is a loose side. So there is a limit for any belt material to have a specific tension. So for a given belt material from the manufacturer's catalog, you can find what is the allowable maximum tension that it can sustain. If you exceed the tension, the belt will snap. The belt material will not be able to withstand that. So imagine this is just like a yield strength of a material or the breaking point of a material. You know what is the ultimate tensile strength of a material. Similarly, for the belt material, we are basically working with allowable tension. This is generally provided per unit width of the belt. So you can calculate, you can find the F1 allowable from the manufacturer's catalog by selecting a belt material. That's step number 3. Step number 4 is that if you select a belt material and you know what is the maximum allowable tension, you can find what will be the loose side tension, because you know that F1 minus F2 is equals to 2T divided by D. That is basically the expression we actually saw. So just let me basically show you here. When we begin with, we started with this expression. Remember, torque transmitted is delta F times the radius, which is a torque. So torque is F1 minus F2, tight side tension minus loose side tension times radius. So F1 minus F2 will be 2 times tau divided by D. That's what I'm writing it here. Is it making sense, guys, so far?
Yes.
Yeah. So basically calculate F2, which is from this expression, F1 minus F2 is 2T over D. Using this expression, calculate F2, and where F1, this is allowable. So use F1 allowable, put in this expression, find F2, determine F2. And then the last step is, step number 5 is use belting equation, which is F1 minus FC, F2 minus FC is equals to exponential F theta as F coefficient of friction as 1 over angle of wrap, natural logarithm, F1 allowable minus FC divided by F2 minus FC. So use belting equation to determine or calculate the coefficient of friction, required coefficient of friction. This is the required coefficient of friction if you have to deliver torque and power from this shaft to this shaft, from this side to this side, with a specific efficiency, with a specific RPM, omega input, and with a specific velocity ratio. So given these design parameters, you can basically find out what is the amount of friction coefficient required for this belt material. So when you select a belt material from manufacturer's catalog, it will not only give you this, but it will also give you F coefficient of friction from the catalog. So let's say this is the catalog version. So this is the coefficient of friction that you will get from the catalog. Now, if the required friction coefficient, this is the required, if F required is less than F catalog value, that means your design is safe. That means whatever the belt material you have selected is going to work in this case. If it is not, then you have to go with a new belt type of belt material to go with the higher coefficient of friction, higher belt tension, and do the same calculations and find out what is the required coefficient of friction. Making sense or not? Yes. Let me recap here. Recap the steps. So that will help you to understand that. But whatever the framework that I'm basically writing it down here, it will remain the same whether it is a flat belt drive, whether it is a V belt drive, whether it is a flat belt drive, any belt drive that you can come across will actually go through these specific steps, where basically you need to know what is the center distance between the input and the output, what is the velocity ratio, what is the efficiency, what is the power input that you are transmitting. So these are some of the inputs you need. What is the angular velocity of the input side? So using those inputs, what you have to do is you have to first calculate the angle of wrap of the belt around the pulley. Then you have to find what is the amount of torque that is going to be supplied, because it depends on the power, input power divided by the rotation velocity. Also, you then thereafter, you have basically start with a belt material. Any belt material you can begin with from the catalog, just like you begin with any material of your choice for your design. You have to select a belt material from the manufacturer's catalog, and that catalog will give you what is the maximum tension that belt can accommodate and what is the coefficient of friction that belt will have for a given surface contact. So it will give you two values. You will work with one value here, F1 allowable, and you proceed to calculate what should be the loose side tension for the given torque input. For the given torque requirement from step number 2, how can you calculate the loose side tension, which is in this relationship. Once you get F2, then use belting equation to calculate your friction coefficient, required coefficient of friction. Once you get that, then match it with the catalog value. If the friction coefficient, for example, say it comes out to be 0.5, but the catalog value is only 0.3, then you know that this belt material will not be able to withstand or provide the torque transmitting, because the required coefficient of friction is 0.5 and the catalog value is 0.3. That means you have to go with another belt material that will give you at least 0.5 friction coefficient. Or it changes increase the tension of the pulley to reduce the friction coefficient somehow. So basically you have to go through that iterations of the design again, calculating again. But let me know if this framework makes sense to you or not.
Yeah.
Any questions from anybody so far? Is everybody following it? Following all the steps we actually mentioned in here?
Yeah, so far it's making sense.
Yeah.
Great. Okay, so that basically wraps up our the design process or design steps for selecting a belt drive. I mean, there will be some homework problems that you will get in the next round of homework and homework set, and you will basically experience the calculation steps there, and you do the calculations yourself. You will understand the process better. but the framework of the design or basically selecting a belt drive for a given design scenario remains the same. Now, one thing that we have not yet covered in this whole discussion is what is the role of initial tension. If you have probably have heard about the belt is getting loose, so you need to tighten it, right? Somehow you have somewhere you have come across this concept. So basically you need to provide a initial tension for the torque to be transmitted. So what is the role of initial tension? Let's call that as Fi. So we'll see that role here. So let me again draw a schematic of the smaller pulley. Being given, yes.
Real quick, sorry. If you go to the very end of your last page of notes, it said the statement that said f of what is that f? What was the subscript? F that one?
Required REQ, required coefficient of friction, and catalog value is here. This is the catalog value. If F required is less than F catalog, your design is good. Otherwise, you need to change the belt material.
Okay, cool. Thank you.
Okay. If this is the case, then change the belt material. But if it is less than F catalog value, that means your design, your belt material you have selected is safe. So you can work with that. That will help you for your torque transmission, power transmission. Any questions, other questions from anybody else? Okay, if not, then I was just showing you the role of initial tension here. So we know that now that we have got, sorry, F1 here, tight side and loose side. So basically this has a component which is initial tension plus Fc plus minus delta F over 2. And this has component Fi plus centrifugal force plus delta F over 2. And what is basically this is nothing but you know that F1 minus F2 is 2T over D, which is torque divided by radius, and basically means that delta F is T over D. So torque divided by diameter is your delta F. So what it basically says that the loose side tension has these components: initial tension, centrifugal force, and our delta F. Delta F is coming because of the torque being transmitted. And this is a tight side tension. Tight side tension has three components again: initial tension, centrifugal force because of the rotation of the pulley. This is rotating with angular velocity omega. So the belt is also having that rotation, and that causes it to experience some centrifugal force. And then delta F over 2 is basically the difference because of the torque being transmitted. So what you actually do is, if you actually sum this up, you will find that F1 plus F2 is equals to 2Fi plus 2Fc, or Fi is equals to F1 plus F2 divided by 2 minus Fc. So what it basically says that the initial tension in the belt has to be equals to the average of the loose side and tighter side tensions minus the centrifugal force of the belt is experiencing because of the rotation. So what it actually says that if I actually further expand that, what I will actually see that I will get an expression for initial tension in the belt and the tighter side and looser tension of the belt. So this is your belt tension versus initial tension in the belt. And what it says that if Fi is 0, this is Fc, this line is F2 loose side tension, and this line is tight side tension. So if I plot the tight side tension F1 versus Fi, I got this line, And if I plot loose side tension versus Fi, initial tension, I got this line. And what it says that if my initial tension is 0, which is at this point, then what I will get is F1 and F2 are both equal. So in that case, F1 and F2 will be both same. In that case, what will be delta F? F1 and F2 are both same. What will be delta F then?
0.
0. And if delta F is 0, what will be torque being transmitted?
0.
0, right? So this is the point what is saying that if my initial tension is 0, if my initial tension is 0, in that case, F1 is equals to F2, and in that case, equals Fc. In that case, T is equals to 0. So torque cannot be transmitted if my initial tension in the belt is 0. So this initial tension becomes the very important factor in deciding how much torque can be transmitted. Very important factor. For example, if my Fi is this value, let's say this is MI value, and corresponding to that, the difference between F1 and F2 will be your 2T over D. So this is the difference between F1 and F2, tight set tension and loose set tension. This difference is equals to 2 times the torque divided by the diameter of the smaller side tube. Are you guys getting what I'm saying here? Okay, if you are not following it, let me just wrap up this lecture with this figure. This is very, very important figure, basically, to understand the bell drives. What it is saying, sorry, and any question in here?
Yeah, can you, I mean, I guess you're going to, but can you, I just didn't really catch what you were saying on the left side. So
this one.
Yeah, so the F1 is equal to F2 and all that. Yeah.
Yeah, so what I was saying that if my Fi is equals to 0, then what I will have is delta F is 0. Then what it basically means both the loose side tension and the tighter side tension is the same. Okay, what I was trying to explain, that will help you earlier. So let me actually explain this figure. What I was saying in this figure is very important. And what this figure is showing, it is showing the belt tension. These are tensions in the belt. Tight side tension, loose side tension. Everybody agrees with that part? This is a tight side tension, this is a loose side tension. Everybody agrees with that part?
Yeah.
Yeah. If I plot these tight side tension, loose side tension as a function of initial tension in the belt, I get this curve. One straight line over here and one straight line over here. And what is basically saying that the tight side tension will keep on increasing if my initial tension keeps on increasing. So if my initial tension is 0, tight side tension is equals to Fc, which is given by, Fc is given by this expression, mr square omega square. R is nothing but d over 2. Omega is angular rotation, mass is a mass per unit length. This is basically the expression. So if my initial tension is 0, my F1, the tight side tension will be equals to Fc. The loose side tension will also be equals to Fc. So both F1 and F2 will be equals to Fc. And if that is the case, then torque, which is F1 minus F2 times d over 2, is equals to 0. Are you guys getting what I'm trying to say here?
Yeah.
And as the initial tension keeps on increasing, so from 0 to, let's say this is 5, this is 10, this is 15 newtons, this is 20, this is, like I said, keeps on going, and this is 100 newtons. So as I keep on increasing my initial tension in the belt, I see there is a difference between the two tensions. So that difference basically will be the one that will help me to decide how much torque can be transmitted. So if my initial tension is 20 newtons, I can transmit this much torque based on the difference. I know the difference between F1 and F2. That should be equals to 2 times T over D, because I know the radius. So I know T is equals to F1 minus F2 divided by, multiplied by D over 2. So I can find what is the torque to be transmitted at this point. If my initial tension now goes from 20 newtons to 100 newtons, I know what is the difference I'm going to get between the two sides, and I can find the torque according. So torque keeps on increasing depending on how much initial tension is there. So if initial tension is 0, torque transmission is 0. If initial tension is 20 newtons, torque is given by this difference. If my initial tension is 100 newtons, the torque is given by this difference. Does it make sense? Yeah? Are you guys with me?
Yes, Professor.
Yeah? Everybody is understanding. This is a very, very important, I mean, the summary part of understanding the belt drives, how the belt work or belt drives work. They work basically because of this initial tension. If the initial tension is 0, there is no torque getting transmitted. F1 and F2 both will be the same. And if both forces or both tensions will be the same, then we know that there cannot be any torque being transmitted because both forces are basically the same. So initial tension is a key here. If you keep on increasing the initial tension, the amount of torque transmitting capacity keeps on increasing. But there is a limit. You cannot just go on doing that for like how long can you go? So that depends on the belt material. So I know that the manufacturer allows me a specific maximum value. Manufacturer says that there is a specific limit on a given belt material. So let's say the manufacturer says this is the maximum tension that you can go. So that means you can only get to this part where you can only apply this much maximum initial tension. Because if you go beyond that, the belt will snap. Does it make sense, guys?
Yes.
Yeah, makes sense.
Yeah. So that is what it's, I mean, I will basically stop our discussions at this point of time. I mean, I don't know how much time is left. Almost there. So let me quickly, if there is some few minutes more, I can quickly go through the slides because this is actually exactly what we have gone through in the document. So let me quickly go through the slides and it will help you to understand. So this is nothing but the expression for, okay, these are the expressions for calculating the angle of wrap, as I was mentioning how to get the angle of wrap. L, as you just rightly pointed out to me, is the total length of the belt, the wrap being wrapped. This is for round belt drives. There are some reversing drives. We actually gone through this. So this is the mechanics we actually went through, finding out that, okay, how to estimate the normal reactions, the centrifugal force, the frictional force, and the tension on the two sides, and how that is related to the friction coefficient. This is the belting equation I was basically referring to. F1 minus Fc, which is mr square omega square, divided by F2 minus Fc will be your exponential times friction coefficient times angle of wrap. And this is what we actually see, that these individual forces on the two sides are comprised of initial tension, the centrifugal force, and the amount of the delta as a small increment in the forces that you actually will see. Now, here the plus and minus will be a bit reversed because the torque being supplied, we actually applied a clockwise torque. Here you see a counterclockwise torque. That's why you have tight side on the upper end and the loose side on the bottom end. So that will be that will change depending on how your torque is being transmitted. So this is the last figure I was basically showing you. It is basically showing how F1 and F2 varies with Fi, the initial tension, and these two lines are for the belt tension. This is a tight side tension and this is the loose side tension. And if my initial tension is 0, I will have F1 and F2 both equals to the same, no torque. But as Fi keeps on changing, the difference between the two lines will define how much torque can be transmitted, which is this gap, which is this expression. And there is a maximum limit because you cannot just keep on increasing the initial tension because there is a maximum limit for the belt tension from the materials catalog or manufacturer specification, and this is the maximum limit you can basically reach. So that is what this equation or this belt tension versus initial tension graph actually shows. Thereafter, I guess I'm just skipping through these slides. You can basically go through them. We actually gone through each one of them, except there are some tabular values. These are steps for deciding on the price, which is basically all the 5 steps I mentioned. There's one more basically depending on calculation of this speed FC basically. That's what I was mentioning. If F required is less than F actual, then you have a belt drive which is properly selected. If not, then you have to change the belt material and belt specification for that's what we were actually discussing. Okay, there are some belt tensioning schemes. Uh, and there is one more about the variation of belt tension. So we will actually go through these two remaining slides in the next lecture. I think it will be a lot of information for you guys today. So I will begin with few remaining slides in this lecture in the next time when we will meet. But to summarize, these are the basic steps for selecting a belt drive for a given requirement for a given design application. And this is the important slide which tells you how the initial tension plays a role in defining or deciding how much torque can be transmitted. So initial tension is the key here, and based on as the operation, because of the operation service life, the belt keeps on loosened. So you need to have some provision for increasing the tension or basically tighten the belt. So when we say the belt gets loosened, you basically need to provide the right amount of initial tension, because otherwise the torque will not be transmitted, the desired efficiency will not be reached. So that is why you need to have a proper initial tension in the system. So we will actually continue our discussion in the next lecture from here onwards, and hope to complete the belt drive. And next lecture we will be focusing on bearing design, bearing selection and bearing design.